Okay, so just a reminder, we ran an experiment for a particular threshold and a particular pair of distributions, and I don't know, these are the numbers we got, and that corresponded to estimate epsilon of 1.03. Okay, but then, we can run the experiment again, and of course, we would get a different set of outcomes, and it will end up with some other epsilon, 1.22, much higher. So, which one is it? Like if someone claimed that their epsilon for this particular delta is, 1.1, and we ran this experiment, we will tell them, aha, we caught you, you're lying. It's actually higher. But then you might as well run it and get a lower number. So what is happening here? And the answer of what is happening here is simply, this is an experiment. And like any experiment, like any empirical attempt to evaluate some property of some underlying distribution based on a draw from that distribution, we cannot be sure what the actual value is. We need some confidence intervals. So what is the language, what is the mathematical language that we need to use here in order to identify whether this is indeed a privacy violation or not, whether this is the correct epsilon or not? So here's a hint. This is a term we're using already for a lecture and a half. No, hypothesis testing. Now, we're doing hypothesis testing in the classical statistical meaning. We ran an experiment. Our null hypothesis is the mechanism is epsilon dp for some epsilon, and we ask, what is the chance that we will succeed significantly more than what it predicts if it is epsilon? You can also think of it as sort of more like a regression problem, because any auditing can be formalized as like one of two perspectives. One is someone claimed they are epsilon equals something, delta equals something dp, and my experiment has the potential to refute that claim. And another option is someone just gave me a mechanism, and I'm running this experiment to say, well, look, your epsilon is at least this value. The first one is more closer to a classification problem or hypothesis testing. The hypothesis is that it is indeed epsilon equals something dp. And the second one is a bit more like a regression problem, where we say, well, let's estimate epsilon. Again, a lower bound on epsilon, but lower bound now due to the choice of data sets and decision rule, but let's say we fix them. So it's an estimation of a lower bound on the privacy. Right? Either way, what can we hope for? So let's look back at this experiment. Right? This looks very jagged, but we know that we can improve it. Right? If I increase the number of samples, then things become a bit more cleaner. And if I increase it further and further and further, things become, look nearly smooth, and these distributions look relatively nice. And probably now, if I run the experiment many times, so look, now the estimation is 0.98. I run it again. Look, the number is practically fixed. So we know that the larger the sample size, the better the estimation. How well does my estimation, how well does it improve? How quickly does it improve as a function of the number of samples? So let's think about it. Let's look at this distribution. What happened here? This is the real world. So I ran a certain number of experiments on column negative and a certain number of experiments on column positive. What is an experiment here? I simply drew a value from the distribution defined by dataset 1 and dataset 2. Okay, so each one of them I drew 500 examples in my case. Okay. Let's say the true value of the false positive rate, which is basically the proportion of the false positive cell out of the truly negative column. Let's say the true rate is 0.1. Now, what is the distribution of possible ratios I will actually experience? It has a name, this distribution. What kind of distribution is this? This is a binomial. Why? Because every experiment is independent of the previous ones. Each one of them has false positive rate probability to land in false positive and true negative rate to land in the true negative. So the number of values I'll have here is the binomial, and if I normalize it by the number of experiments, this is the distribution of the false positive rates. And we know that this distribution is concentrated around the true mean using some of the classical concentration guarantees. So the best you can do is Chernoff. Hopefully also achieve something similar, depending in what parameter regime. So basically, we can create confidence intervals. We can say that if I ran an experiment and got whatever it is, right? Let's look here. Here I got 19 out of 500 is my empirical false positive rate. All right? So now I'm not asking, given a false positive rate, what is the probability of getting this empirical result? But the other way around. So I don't ask probability, right? I don't have a prior, but I can say, if I will add some confidence intervals, what is the probability that I would get a result such that the true value does not land within that confidence interval? This is what confidence intervals are. And we have the expression. Okay, so what does it look like in practice? This is what it looks like. So let's understand this picture. So now we're back to the ROC point that we had before, and this is what we got as a result at the end of the experiment. We ran a bunch of experiments, some with a positive one, some with a negative one, and we got a concrete number. Now, zooming in, looking here, this is the number we got. But we know that both its x value and its y value are noisy estimates of the true false positive rate and true negative rate. True false positive and true positive rates. Right? The x-axis is the false positive rate. The y-axis is the true positive rate. There is a real value, and we sampled a point where the x-axis and y-axis are binomially distributed around the real point. So if I got this green point, I know that with high probability, for some fixed probability, the true unknown point corresponding to the false positive rate and true positive rate lies somewhere in this rectangle. Actually, you can have slightly tighter bounds that are not a rectangle, right? The rectangle is basically, I'm having one confidence interval for the denominator and one for the numerator, right? Because the x and y axis, the ratio, it's two values, but I can actually do better. But that just improves in the constants, not in the asymptotic. So for simplicity, I'm keeping it this way. Also, I would point out that this is asymmetric, and that is because I'm not using here Hofdingen bound, but Chernoff bound, and Chernoff bound is asymmetric when you're very close to the extreme small values. But whatever, there is some box. So, what is the best So what is the strongest bound I can now give based on that? So first of all, it's already clear that I cannot hope that with any finite number of experiments, I can say with perfect certainty your epsilon is at least something. I would not be able to say that. So now we have a third parameter, let's call it some alpha, which, notice, this is somewhat confusing because we're talking here about distributions. So alpha is the probability that I will incorrectly estimate epsilon, where epsilon itself corresponds to some ratio between two other probabilities. So it's a bit annoying. But the alpha here basically corresponds to the size of the rectangle, right? Because the smaller the alpha, the smaller the error I'm willing to accept, the bigger I need to increase this rectangle. But whatever, there's some alpha that I fix. I say I want to do this accounting such that I will not blame a mechanism for not being sufficiently private with probability greater than 95% or 99%, right? The error rate that is small enough. Okay, so I got this point, and now I know that, well, with high probability, the true point on the ROC is somewhere within this range. Okay, what is the biggest claim I can say? So, which one of them is a bigger, how do you call it? A more severe claim? Which one of them implies worse privacy? Further up or down, further right or left?
Worst privacy. Top left is the worst privacy.
Right. Because that is the furthest away from the diagonal. So if I take this point and I say, well, it's one of those points. So the further I go here, the more severe my privacy, the privacy violation I suspect. The further I go here, the less severe it is. So if I want not to be incorrect by more than some probability, I cannot take any bigger claim than this bottom right corner. Okay? So this is basically what happens here. Privacy auditing, as I said before, but with this statistical correction. So let's see what it looks like in practice. So here we have a specific epsilon equal, in fact, 0.7 something, almost 0.8. And there's the distribution, and you get a particular threshold. Sorry, this is not the epsilon. This is the
Distribution.
No, sorry. This is the distribution of epsilons, where when I say epsilon, I already mean I fix delta, I compute and the threshold, and I compute false positive and true positive rates, and all of that, and that derives a particular epsilon. Like I'm running already, every point in this experiment basically corresponds to a full experiment here, right? Of, well, there's some threshold, and therefore, and some delta, and then I ran a bunch of experiments, okay? So, and the true epsilon, had I ran it for infinitely many times, would have come out to be 0.79, whatever. And then I ran the experiment, and what epsilon did I actually get? So, I would get the blue distribution. This is the empirical distribution. You're not surprised, it's unbiased. Right? It's a nice distribution. It's concentrated around the correct value. and it's about symmetric, yeah, give or take. Great, it seems like it's a good estimator. But if I use this to blame people for not being sufficiently private, half of the times I will blame them for no good reason. But if I add this failure probability term correction that shifted my estimations, right? This is not a perfect shift because, as I said, I changed somewhat both the numerator and the denominator, but it's some correction term. And now, as you see, I have very few errors. As you can see here, the number of errors is slightly below the probability due to what I said. This is somewhat loose in the fact that I took both in the numerator and the denominator. But basically, you can see that as I increase alpha, the number of mistakes grows, and as I decrease it, the orange distribution basically shifts further to the right. Again, more experiments, less experiments, everything is what you would expect. And this is basically how we can do privacy auditing. So, just to recap, differential privacy guarantees something on the ROC. I mean, it can be interpreted in other ways, but also on the ROC, between a specific pair of distributions, and any decision rule will correspond to a particular point, and then I can run that experiment. And up to the statistical correction, I know that at least for some pair of distributions and for some decision rule, I get this epsilon, therefore it's a lower bound on epsilon. So from now on, in the next few lectures, when you will try to start developing more and more sophisticated mechanisms, we'll say, oh, we'll do first this step and then that step, and we'll train something in one way or another way, and then you need to worry, maybe I have a mistake in my proof, maybe there's a mistake in my implementation. There are like all sorts of places where things can go wrong. Maybe the person claiming to run a certain algorithm cheated and it's a different algorithm. Be all sorts of things. I can always just run an experiment. And this is what indeed people do these days with like even big neural networks. You take a particular element that is very atypical, right? Again, we always need to find good candidates, because if you take just arbitrary pair of data sets, they might look very similar. If you replace a usual, typical element in a data set sample from a distribution, probably it will be much harder to identify. That is sort of equivalent to say, what if the difference between the means was not 1 but was 0.1? Well, obviously it's going to be harder to distinguish. So you need to come up with a good candidate for a atypical element. You need to come up with a good decision rule, which is a whole field of research. If I give you a neural network and some image, and I ask you, how do you know if this image was in the training set of this neural network? That's not necessarily a trivial problem. We don't have a simple function that we say, oh, this is monotone in the log probability ratio between the probability of this network given that the element was in the data set or not. But we have all sorts of tricks. One example, you plug in this element into this network as you do inference on this element with this network, and you see what the loss is. And since we know that neural networks tend to memorize their data to some extent, they typically have a loss, even if they're very good in generalization, and the typical loss they get on the population is very low, still the loss that they get on the training set is typically practically zero. So if you see a good accuracy in the sense of it correctly classified the image, that doesn't tell us a lot. Because maybe it just learned to identify images of cats, and well, it identified this is the cat. But if it also got zero loss, then you can say, well, neural networks, even when they're very good, they're not 100% confident on their prediction. They're just like relatively confident, but the elements that they saw, they perfectly memorized, and then they will be perfectly confident. So here's an example of what can you expect to be a good decision rule. But you can come up with other decision rules. Some of them more sophisticated, some of them less. Once you do that, you run the experiment, which, open parentheses, is a nightmare when it comes to neural networks. You will train hundreds or thousands or tens of thousands of times a neural network. That will be challenging, but okay. And there are more advanced techniques these days. But you do that, and you say, look, ran the experiment a bunch of times, and I'm much better in guessing that an element was in the data set when it was indeed in the data set than when it was not. Therefore, I have a point that's very far from the ROC curve, from the diagonal on the ROC curve. Therefore, you're really not private. This is give or take what we do. 2 points I want to mention on this subject before we move on. The first is something I think Nissan mentioned before. What I did here is I ran the experiment, I got a threshold, I said this is my decision rule, and I moved on. But who said this is the best threshold? So in fact, when we run 500 experiments from the negative distribution, 500 from the positive distribution, we need to make 2 steps of decision. One is choose a threshold or a decision rule. And step 2, given that, estimate epsilon. If you're not careful and you do the same, both of the decisions on the same day, using the same data set, now you get into the problem of adaptive data analysis, you're reusing your data, your statistical validity degrades, so it's a bit problematic. So either you do some kind of union bound, which is typically quite lossy. Another option is you split your data. You take half of the data to identify the threshold, and then the other half, data meaning here the 1,000 experiments. So you take a bunch of them to choose the threshold, and then the rest to estimate epsilon. And there are some initial works, which is, I think, a promising question of something that we can squeeze that won't make a huge difference, but still, it is important to understand doing them simultaneously and using more sophisticated statistical analysis tools to justify the validity. That's the first point. Second point is I want to point out the fact that you might have already noticed that this circle corresponding to the point on the ROC, which induces the epsilon, typically lands relatively close to the 0, corner. And in fact, even the fact that it's a bit further away is only because I chose a relatively large delta. If I will start decreasing delta, what would happen is, you see, this is now like nearly the first point. And if I will move it further, what will happen is the epsilon will become infinity because I'll have like an extreme one. So let's see, okay. So it's even with 5,000 examples, you will see I can move further, and then at some point here. Now it's infinity. But let's look here, here, okay. This is an extremely low point. This should not surprise us. Why? Because what is the expression that we have for epsilon up to this small delta? It's a ratio of true positive rate, the y-axis, the false positive rate, the x-axis. What is the best way to get a large ratio? To decrease the denominator. So think about it. What kind of point here will be able to induce a large ratio? Only if the ROC is really terrible. But here, it's relatively easy to have just at the very, very beginning, a very steep slope to induce a significant epsilon. And indeed, Gaussian is a good example. When you look at it, Gaussian doesn't look very bad. Or let's even have, let's take this one, okay? This looks like a relatively good ROC curve. Actually, much better than this one. But here, epsilon is equal 1. Here, in the Gaussian case, if I start decreasing delta sufficiently, epsilon keeps increasing and increasing, and we know it, right? Gaussian is not pure dp. So what is happening here? The thing is, the trade-off function is really nice, but at the very, very, very small values, what we have is a extremely large slope, which induces a large privacy. So this is a reason why when you do privacy auditing, you would tend to push towards the extreme small false positive rate and small false negative, true positive rate. Because this is where you'll get the large ratio. But what is the problem with this idea? Why shouldn't I take like the first point here, right? Like if I'm looking here, you see I'm trusting nearly the first one. Why is it not a valid choice?
Small sample size.
Exactly. So the annoying part here, and this is one of the biggest challenges of auditing, is that the two properties are fighting against each other. On one hand, the strongest privacy violation can be found in the most extreme case. What does this case correspond to? It corresponds to a world where you nearly never guess positive, one way or another, and therefore the percentage of cases where you guess positive either correctly or incorrectly, both of them are very small, and then the ratio can be big. But if there are very few examples, then your statistical validity ruins you, right? Because basically you shifted your ROC. So in practice, one of our biggest challenges is how to push auditing to the extreme so that we will be able to do it with like not negligible data set, but like relatively small data set. And we would have most of our samples in a way concentrated around here. Because if I guess positive only once in 1,000 experiments, that means that effectively I need to run 1,000 experiments for every sample I get from the relevant statistic. So how to do better, this is the big part of the ways we currently work on improving auditing. I think we'll leave it here. Questions? Good? Yeah.